Hi everyone, and welcome back to another episode of the We're Gonna Make It podcast show, your go-to podcast for all things emerging tech. Today, we've got something truly exciting for you. We're diving deep into the latest research report by Meta on their groundbreaking Llama 3 foundation models. Trust me, you don't want to miss this. Let's start with the basics. Foundation models are the backbone of many modern AI systems. These models are designed to handle a variety of tasks across language, vision, speech, and much more. Think of them as the Swiss Army knife of AI, which is capable of supporting a wide array of applications altogether. Now, the development of these foundation models happens in two main phases. The first, there's the pre-training stage. Here the model is trained on massive datasets with simple tasks like predicting the next word in a sentence or captioning an image. It's like teaching the model to read and understand the basics of language and context. The second stage is post-training, and this is where the magic really happens. The model is fine-tuned to follow instructions, align with human preferences, and improve specific skills like coding and reasoning. It's like taking a talented student and giving them specialized training to excel in their field. Meta's latest innovation, Llama 3, brings some significant advancements to the table. The Llama 3 herd of models supports multilinguality, coding, reasoning, and even tool usage. Their flagship model boasts a whopping 405 billion parameters and processes information in a context window of up to 128,000 tokens. That's like having a conversation with an AI that remembers everything you've said and more. So what makes Llama 3 so special? Well, Meta identified three key levers for developing this high-quality foundation model: data, scale, and managing complexity. They've optimized each of these areas to create something truly remarkable. First, let's tackle data. Compared to the previous versions, Llama 3 uses a much larger and higher quality dataset. We're talking about 15 trillion multilingual tokens from pre-training, up from 1.8 trillion tokens used to train Llama 2. Meta has also developed more rigorous pre-processing and curation pipelines for better data quality. Next, let's pick up scale. Llama 3 is trained for a far larger scale than its predecessors. The flagship model alone was pre-trained using 3.8 into 10 to the power 25 flops, which is almost 50 times more than the largest version of Llama 2. With 405 billion trainable parameters and 5.6 trillion text tokens, this model is a true powerhouse. Finally, managing complexity. Meta has made strategic design choices to maximize their ability to scale the model development process. They opted for a standard, dense transformer model architecture with minor tweaks for stability and efficiency. Their post-training process is relatively simple, focusing on supervised fine-tuning, rejection sampling, and a direct preference optimization instead of a more complex reinforced learning algorithms. We've talked about these algorithms in our previous episodes as well, so do check them out. So what has been the result after all of this? Well, Llama 3 is a set of three multilingual language models with 8 billion, 70 billion, and 405 billion parameters. These models have been evaluated on a wide range of benchmark datasets and have performed exceptionally well. The flagship model in particular is on par with the leading language models like GPT-4 across various tasks. Plus, Llama 3 offers a better balance between helpfulness and harmlessness compared to its predecessors. Meta is publicly releasing all of these three models under an updated community license. This includes pre-trained and post-trained versions of their flagship model and a new version of their Llama Guard model for input and output safety. This open release aims to spur innovation and accelerate development of artificial general intelligence in a much more responsible way. But that's not all. Meta is also developing multimodal extensions to Llama 3, enabling capabilities like image recognition, video recognition, and speech understanding. These extensions are still under active development and not yet ready for release, but the initial results are quite promising. Now let's dive deep into the specifics of how Meta pre-trains their language models, including the new Llama 3. This is where things get truly fascinating as we peel back the layers of what's going into crafting these such powerful AIs. First of all, the data. Imagine having to sift through vast amounts of information, curating and filtering to get the best quality material. Meta sourced their data from a wide range of inputs, making sure to remove any personally identifiable information and adult content. They use advanced deduplication techniques to ensure that what the model learns from isn't just a bunch of repeated information. And this isn't just about gathering data per se, it's also about refining it to the highest standards. Next, they tackled the challenge of web data curation. This involved extracting text from raw HTML, ensuring that they preserved important structures like mathematical content. Meta even built a custom parser that outperformed popular third-party tools in retaining valuable information while stripping away the unnecessary fluff. A significant part of their process was dealing with duplicates at various levels, from URLs to individual lines of text. They also employed heuristics filtering to weed out the low-quality documents and outliers, making sure that the most relevant and clean content made it through. This level of meticulous attention ensures that model learns from the best examples available, enhancing its understanding and performance. But they didn't just stop there. They also use model-based quality classifiers, including fast text and more advanced Roberta-based classifiers, to assess and select the best quality tokens out of the bunch. This was crucial in refining the dataset, particularly for specialized domains like code and mathematical reasoning, where precision is absolute key. Speaking of specialized data, they went further by developing domain-specific pipelines to extract relevant content. Whether it was for STEM reasoning or code, these pipelines ensured that the model had a rich and varied diet of information essential for building a robust understanding across different fields. Another intriguing aspect is the multilingual data processing. Meta implemented language identification and filtering to ensure quality of non-English content. This multilingual capability is vital for a truly global perspective, capable of understanding and generating text in multiple languages. Further, determining the right data mix was another complex challenge. They used knowledge classification and scaling law experiments to balance the different types of datasets. For example, they had to decide how much weight to give to general knowledge versus more specialized content like mathematics and code. Their final mix included 50% of general knowledge, 25% of mathematical and reasoning data, 17% of code, and 8% of multilingual content. This careful balancing act helps the model excel across a broad range of tasks. Now, let's talk about the model architecture itself. Llama 3 uses a dense transformer architecture, which, while standard, has been optimized in subtle but impactful ways. For instance, they introduced grouped query attention to improve inference speed and reduce memory usage. They also employed an attention mask to prevent cross-document self-attestation, crucial for handling long sequences effectively. In terms of scaling laws, Meta didn't just look at increasing the number of parameters. They also explored the optimal balance between the model's size and training data using sophisticated scaling experiments. This helped them predict how their flagship model would outperform on real-world tasks, ensuring that they got most out of their compute budget. The infrastructure supporting Llama 3's training is nothing short of monumental. Imagine coordinating up to 16,000 GPUs, each with 80 GB of memory, all working together seamlessly. This setup includes robust networking and storage solutions designed to handle enormous data throughput and computational demands. To efficiently train such a large model, they use a combination of tensor, pipeline, context, and data parallelism. This approach allowed them to scale the model effectively across thousands of GPUs, optimizing both memory usage and computational efficiency. They even implemented context parallelism to manage extremely long sequences up to 128,000 tokens, which is a feat in itself. And the training process was meticulously planned as well. They started with a lower batch size for stability and gradually increased it to a model trained on more data. This careful tuning helped them avoid issues like model divergence, where training goes off the rails itself. In the final stages, they introduced long context pre-training, gradually increasing the sequence length the model could handle. This is crucial for tasks that require understanding context spread over long passages of text. Lastly, they employed a technique called annealing, which involves fine-tuning the model's learning rate as training progresses. So this coupled with Polyak averaging, where they average multiple model checkpoints, helped in stabilizing and refining the final model itself. Now let's look at the post-training side of things, ensuring that they are finely tuned to meet the real-world needs. This process involves several crucial steps that significantly enhance the model's performance across various tasks. Post-training begins with a unique step. Using a reward model that is trained with human-annotated preference data, this model evaluates and scores different responses, helping to align Llama 3 more closely with human expectations. Now, the reward model's training involves a meticulous process where responses are ranked based on preference, allowing the model to learn which types of responses are considered better or worse. To support this, a new chat dialogue format is introduced, which includes special tokens to guide the conversation flow, especially important when the model has to use tools or handle multiple turn interactions. This format helps the model understand where to direct the responses, whether to a user, an internal process, or even a function. The reward model itself is built on extensive human annotated data, which includes not just preferred and rejected responses, but also an edited category where responses are refined for better clarity or accuracy. This three-tier ranking system helps the model distinguish subtle differences in response quality, making it better at producing nuanced and accurate replies. Following the training of the reward model, the process moves into supervised fine-tuning phase. This phase involves using the reward model to filter through vast datasets of responses, retaining only that meet the highest quality of standards. Now, this data includes human annotations, synthetic data, and responses selected through a technique known as rejection sampling. In rejection sampling, multiple responses are generated, and the best ones are chosen on a predefined criteria, ensuring that the training data is rich and varied. The next thing is direct preference optimization, which further refines the model by aligning it even more closely with human preferences. This method uses the most recent batches of preference data to fine-tune the model, ensuring that it stays up to date and with latest standards of accuracy and quality. DPO also incorporates regularization techniques to stabilize the training, such as masking out formatting tokens that could otherwise skew the model's learning process. A significant part of the post-training involves careful data curation. The data used for training is not only diverse, but also rigorously cleaned and pruned to remove low-quality samples. Now, this includes eliminating excessive informal language, repetitive phrases, and other undesirable patterns that could degrade the model's performance itself. Additionally, data is scored based on complexity and quality, ensuring that the model is trained on both simple and challenging tasks, which is crucial for developing robust capabilities. Special attention is given to enhancing specific skills such as coding, multilinguality, and reasoning. We had a discussion about this before. For coding, the model is trained using a dedicated code expert version of Llama 3, which has been fine-tuned on massive datasets of code snippets, problem-solving tasks, and debugging exercises across multiple programming languages. This training is supplemented by generating synthetic data where the model learns from its mistakes through execution feedback loops, thereby improving its coding accuracy and fluency. In the area of multilinguality, Llama 3 is refined using a dataset rich in both human annotated and synthetic examples across various languages. This ensures that the model can perform well in different linguistic contexts, addressing challenges like translation quality and cultural biases. The data mix includes high-quality multilingual text, some dialogues, making Llama 3 versatile in handling queries in multiple languages easily. For the mathematical reasoning and logic, the model is trained to handle complex multi-step problems, generating detailed explanations and justification for its answers. This capability is enhanced through techniques like chain of thought reasoning, where the model learns to break down the problem into smaller, more manageable steps. Additionally, the model is equipped to use external tools like Python interpreters, which allow it to execute code and verify answers, adding a layer of computational accuracy to its reasoning process. The model's ability to handle long text inputs is another groundbreaking feature here. Extending its comprehension from the typical 8K tokens to a staggering 128,000 tokens, Llama 3 can maintain coherence and relevance over extended dialogues or documents, a significant advancement for applications requiring deep contextual understanding. This capability is crucial for tasks like summarizing long documents, handling multi-turn conversations, and analyzing large datasets. Moreover, Llama 3 is trained to use a variety of tools, transforming it from a simple chat model into a more versatile digital assistant. It can interact with search engines for real-time information retrieval, use Python interpreters for complex calculations and analysis, and even employ mathematical computational engines for solving intricate science and math problems. This tool use is integrated into its conversational abilities, allowing the model to execute complex workflows, including multi-step problem solving and data processing. Now, a very important part, which is addressing factuality. Meta has developed techniques to reduce the model's tendency to hallucinate or provide inaccurate information. This involves aligning the model's outputs with verified factual data, ensuring that it can distinguish between known facts and areas where it lacks knowledge. The model is trained to gracefully handle questions outside its expertise, either by stating its limitations or redirecting it to more appropriate sources. And finally, steerability is a critical focus area where enhancing the model's ability to adapt to different user needs and contexts. So through system prompts, Llama can adjust its tone, format, style, and provide responses that are tailored to specific tasks or user preferences. This makes the model highly versatile and capable of shifting between different roles such as a technical advisor, a customer representative, or even a conversational partner. Alright, that was a lot to take, so on a different note, let's dive into the performance evaluations of Meta 3's models and their safety characteristics. First, let's talk about the pre-trained language model evaluations. Llama 3 was put through rigorous tests against various benchmarks to gauge its performance across several categories like common sense reasoning, reading comprehension, math, problem solving, long text, coding, and even adversarial scenarios. So these benchmarks are industry standards, and Meta went an extra mile by reproducing results from competitor models to ensure fair comparison. Llama 3 excelled in most categories, particularly in common sense reasoning and coding tasks, outperforming models of comparable sizes. For example, the Llama 3 8B model consistently outperformed other models in per category win rates and average performance. The 70 billion model also showed significant improvements over its predecessor, Llama 2, especially in most saturated common sense benchmarks. One interesting aspect of the evaluation was the model's robustness. This involved testing how the model's performance varied with changes in multiple choice question setups, such as few short label biases, label variants, answer order, and prompt formats. The results showed that Llama 3 maintained its robustness across these changes, particularly the 405 billion model, which handled these variations quite impressively. Adversarial benchmarks were another crucial area of evaluation. These tests are designed to challenge the model with tricky, potential misleading scenarios. Now, Llama 3 was evaluated on adversarial question answering, mathematical reasoning, and paraphrase detection tasks. While the model showed strong performance in many areas, adversarial scenarios for question answering and mathematical reasoning were notably more challenging, revealing areas for future improvement. Contamination analysis was conducted to estimate the impact of training data contamination on benchmark scores. Now, this involved checking how much of the evaluation data overlapped with the training data, which could artificially inflate the performance metrics. The results varied across datasets, but overall, Llama 3 showed resilience with a significant contamination impact only in specific cases like peak QA and HelloSwag. Moving on to the post-training models now. Llama 3 underwent extensive fine-tuning using high-quality decontaminated data. The post-trained models were evaluated on similar benchmarks, and the results were quite impressive. The 8B, 70B, and the 405B models demonstrated strong performance across various tasks, including reading comprehension, coding, common sense reasoning, and mathematical problem solving. The evaluation also included proficiency exams like GRE, LSAT, SAT, and AP tests. Llama 3's performance on these human design exams was remarkable, often surpassing the other models in accuracy and overall scores. For example, the 405B model showed competitive performance against top-tier models like GPT-4, especially in tasks requiring complex reasoning and detailed understanding. In coding benchmarks, Llama 3's performance was evaluated across multiple programming languages. The model demonstrated high accuracy in generating functionally correct code, significantly outperforming other models in Python benchmarks like Human Eval and MBPP. For multi-language code generation, the results were also strong. There was a noticeable drop compared to Python-specific tasks, indicating room for improvements in broader programming language support. Multilingual capabilities were another highlight. Llama 3 now supports 8 languages, and its performance on multilingual benchmarks like MMLU and MGSM was outstanding. The 405B model in particular outperformed most competitors, demonstrating its ability to handle diverse linguistic context effectively. For long context tasks, Llama 3 was evaluated on its ability to handle extended dialogues and documents. The model's performance on benchmarks like Zero Scrolls and Infinite Bench was superior, showcasing its capability to maintain coherence and relevance over long inputs. This is crucial for applications requiring deep contextual understanding, such as document summarization and complex conversational interactions. Tool use performance was another focus area. Llama 3's ability to integrate and utilize various tools such as search engines, Python interpreters were tested. The results showed that the model could effectively use these tools to enhance its responses, making a versatile digital assistant. Human evaluations also played a significant role in assessing Llama 3's performance. These evaluations provided insights into the model's tone, verbosity, and the understanding of cultural nuances. The results indicated that Llama 3 is competitive with leading models, particularly in multi-turn reasoning and coding tasks, where it often outperformed models like GPT-4. And lastly, the safety evaluation. Ensuring that the model generates safe and responsible content is paramount in this industry. Meta employed extensive safety measures including data cleaning, safety fine-tuning, and red teaming exercises. These efforts significantly reduced the model's tendency to produce harmful or unsafe content. The safety benchmarks showed that Llama 3 could effectively balance helpfulness and safety, maintaining a low violation rate while minimizing false refusals. Now, more on some exciting techniques used to enhance the inference efficiency of Llama 3 405 billion model. The team explored two primary methods: pipeline parallelism and FP8 quantization, both of which are game changers in handling such massive models. Pipeline parallelism is a clever approach to split the model across multiple GPUs. The Llama 3 40B, with its colossal size, can't fit into a single machine's GPU memory, even with 8 NVIDIA H100 GPUs. So the team utilized 16 GPUs spread over 2 machines. On each machine, the high-speed NVLink is employed for tensor parallelism, but across machines where bandwidth is lower and latency higher, they use pipeline parallelism. This method allows different parts of the model to run on different GPUs simultaneously, significantly enhancing the throughput. They also employed micro-batching during inference, which involves splitting data into smaller batches. This technique boosts throughput without requiring a full pipeline flush, which is crucial because it avoids inefficiencies typically seen during training. Now, onto the other one, which is FP8 quantization, which is a fascinating method where the precision of the model's operation is reduced from FP16 or BF16 to FP8 itself. This reduction significantly cuts down the memory and computational costs, but it's a delicate balance because it can affect the model accuracy. The team found that by quantizing most parameters and activations, especially in the feed-forward network layers, they could reduce the inference compute time by around 50%. However, certain layers, like the first layer and the last transformer layer, were left unquantized to maintain model quality. They also addressed potential underflows and errors in decoding the upper bounding dynamic scaling factors using row-wise quantization for better granularity. This method proved effective, with their approach showing negligible impacts on response quality compared to the full precision methods, while delivering much improved throughput latency trade-off. So, in conclusion, these capabilities significantly expand Llama 3's functionality, making it a more comprehensive tool for communication and understanding across different modalities and languages. As we continue to explore the potential of such advanced AI systems, these innovations in speech and language processing mark a significant step forward in creating truly interactive and intelligent digital assistants. Finally, let's now talk about the significance of open source LLMs, exploring some real-world examples and sharing stories that highlight their transformative potential. One compelling example of open source innovation is the story of Hugging Face, a company that has revolutionized access to natural language processing through its transformer library. Hugging Face's open source approach has democratized NLP, providing tools that researchers and developers of all levels can use to build and deploy sophisticated language models. Now, this community-driven effort has led to rapid advancements in development of specialized models for a wide range of applications, from healthcare to customer service. Another powerful story comes from the use of an open source AI in developing countries. In regions where resources are limited, access to proprietary technology can be prohibitively expensive. Open source models, however, provide a level playing field to all. For instance, in Africa, local developers have used open source tools to create AI applications that address unique regional challenges such as agricultural optimization and language preservation. These efforts not only foster innovation but also empower local communities to find solutions that are culturally and contextually relevant. The open source model also encourages collaborative problem solving. Consider the case of COVID-19 pandemic. During the global crisis, open source platforms enabled researchers worldwide to share data, models, and findings rapidly. This collective intelligence approach accelerated the development of predictive models, helping healthcare providers and governments to respond more effectively to the pandemic. It's a powerful reminder of how open source frameworks can mobilize a global community towards common goals, transcending geographical and institutional boundaries. Next, the story of Mozilla and its open source browser Firefox offers another insight. Mozilla's commitment to openness has fostered a vibrant ecosystem of developers and contributors, leading to innovations in privacy and security. Now, this community-driven approach has not only made Firefox a strong competitor in the browser market, but has also set standards that other companies have adopted, showcasing how open source projects can lead to broader industrial changes as well. So, going beyond these examples, let's discuss a novel aspect of open source LLMs, their potential to bridge the gap between academia and industry. Traditionally, cutting-edge research in AI has often been siloed with the academic institutions or corporate labs. However, open source models facilitate a two-way flow of knowledge and innovation. Academics can leverage industrial-scale models to test the theories at scale, while industry practitioners can adopt academic insights to enhance product development. This synergy fosters a more integrated ecosystem where breakthroughs are rapidly translated into practical applications. Moreover, open source LLMs can catalyze ethical AI development. In a world where AI systems increasingly influence our everyday life, from hiring practices to judicial decisions, transparency is of paramount importance. Open source projects can act as a form of accountability where community collectively scrutinizes and improves algorithms. This transparency helps ensure that AI systems are fair, unbiased, and aligned with societal values. As we look to the future, the rise of community-driven AI governance could be one of the most significant outcomes of open source movements. By involving a diverse array of stakeholders in the development and oversight of AI technologies, we can build systems that better reflect the needs and values of global society. This approach might contrast sharply with the top-down control often seen in proprietary systems, offering a more inclusive and democratic model for technological progress. Therefore, the open source approach to LLMs is more than just a technical and philosophical choice. It's a catalyst for societal change, innovation, and ethical development. By fostering a collaborative, transparent, and inclusive environment, open source LLMs pave the way for a future where AI technologies are accessible, trustworthy, and beneficial to all. Thank you all for joining me in this enlightening journey today. If this conversation resonated with you, please like, follow, and share the podcast. Your support helps us grow and continue bringing you these deep dives into fascinating topics. Remember, in this rapidly evolving world of technology, our collective efforts and shared knowledge ensures that we are going to make it. Goodbye.